So hi, I'm Saicharan. I'm a final year at IIT Guwahati and I'm pursuing BTech. So in today's lecture, we are going to discuss Gauss Law. I'm assuming that you all know what and how to calculate electric flux through a surface, as it would have been taught before teaching Gauss Law. So in this lecture, we are going to discuss what is Gauss law and what is the proof of it and some of the applications of Gauss law. Now let's get into this lecture. Gauss law. First, let's see the definition of Gauss law. It is defined as the net electric flux passing through a closed surface is directly proportional to the total electric charge enclosed within that surface. Mathematically, we can see that it is given as surface integral E bar dot dA bar is equals to total charge enclosed in that surface divided by epsilon naught. Here know that this integral is not a normal integral, it is a surface integral, and the left hand side is nothing but the flux through the surface. So before getting into the proof of Gauss law, let's verify it. So now let's take a case where the surface is a spherical surface and there's a charge q at the center of that surface. Now we want to find the flux through this surface. So we know that the electric field lines due to the point charge would be like this. And also all the field lines would be perpendicular to the surface at which they are going out. So if we take a differential dA bar at this point, we can see that the E bar and the surface are perpendicular, which means the dA bar and E bar are in the same direction. So which means E bar dot dA bar is nothing but E bar into dA bar cos 0, which is nothing but E into dA. So now we know that flux is given by integral E bar dot dA bar. We already know that E bar dot dA bar is directly equals to E into dA in this particular case. So which makes this integral a simple integral E into dA, and we know that at a distance r, the electric field due to a point charge is constant. So I mean, in any direction, the magnitude of the electric field due to a point charge at a distance r would be same. So we can bring the E out of the integral, and integral dA is nothing but the total surface area of the sphere, and which is equals to E into the total surface area of the sphere is nothing but 4 pi r square, and the electric field due to this charge is given by q by 4 pi epsilon naught r square into we know that the area is 4 pi r square. So this gives us flux through this surface is nothing but q by epsilon naught. So we now have verified that the Gauss law is giving a correct result. But now let's say if we want to find the flux enclosed through this case, let's take the same spherical surface, and now let us place a charge at some arbitrary point and not the center. Now the field lines, as we can see, the field lines would not be perpendicular to the area. So in previous case, the thing which simplified our integral was the point that the electric field lines and the surface area at that point would be perpendicular, which makes the dot product a simple multiplication, and that made our whole job easier. And even in this point, we can see, in this case we can see that the field would not be same at all the surface points. So which makes the integration to find the flux very difficult. So, but we know that by Gauss law, the flux should be equal to phi q by epsilon naught even in this case. So now how do we prove that? So let's see the proof now. Let's take an arbitrary surface, and now we are placing a charge q inside it. So Gauss law says that the flux through this surface is equals to q by epsilon naught. So now let's take a spherical surface around q with q as its center and the radius equals to r. So now we want to find let's also take a differential area, and the field lines would be something like this. And we know that, and we have also calculated in the previous case that the flux through this dA is equals to E into dA, as E and dA are perpendicular. And this part, let us take this as ds bar, the surface area of the arbitrary surface part. And we can see that the ds and E bar need not be perpendicular in general. So how do we find the flux through ds? And also if the so we can say that the a whole surface flux passing through this whole surface would be equal to the flux passing through that spherical surface, which would be equal to q by epsilon naught. So now how do we prove that the flux through this dA bar is equal to the flux through this ds bar? So if we take if we take that this ds bar is at a distance nr from q, so we can see that this ds bar's perpendicular component would be forming a cone with q. So the ds bar's perpendicular component would be equals to nothing but dA into nr square by r square, n square r square by r square, as the distance as the area would be proportional to the distance from q square. So we can see that the ds bar's perpendicular component would be equals to dA bar into n square. So this ds bar's perpendicular component is perpendicular to the electric field at that point, and we know that the electric field at that point would be equal to q by 4 pi epsilon naught whole square. So now the flux through ds would be equal to E bar dot ds bar, which is nothing but E into the perpendicular component of ds. We have calculated the E to be q by 4 pi epsilon naught into n square r square into the perpendicular component of ds is nothing but dA into n square. So this comes out to be q into dA by 4 pi epsilon naught r square. So this is the flux through ds, and we already know that the flux through dA is equals to q by 4 pi epsilon naught r square into dA. So we can see that phi of ds is equals to phi through dA. So we can say that the flux passing through this whole random surface is equal to the flux passing through that spherical surface. So what I'm trying to say is the both flux would be equal, and we know that the flux passing through that spherical surface is nothing but q by epsilon naught, as we have already calculated this in this case. So now we also from this we can say that the flux passing through the random surface would also be equal to q by epsilon naught. So hence this Gauss law is proved. So now for an easy analogy, consider, for some easy understanding basically, consider a surface, and now we have placed an object at this in this surface, and the object is firing 12, let's say 12 bullets. So how many bullets would come out of the surface? It's easy, right? Whole 12 bullets would come out of the surface. And now if the object, let's say the object is placed somewhere else, and even in this case all the 12 bullets would come out of the surface. But if we would have a small hole in this surface, we can't say that all the 12 bullets would come out of the surface, as some may pass through that hole directly and go, which would not result in the net flux. So it's important that you note Gauss law is applicable for only closed surfaces. So now if we take a random surface and if we place this object in this random surface, even in this case we would say that the 12 bullets would come out. So what I'm trying to say is the flux would not depend on the surface, but rather it would depend on how many objects are placed inside the surface and what's the magnitude, or what the number of in this case what's the number of bullets it's firing. So flux would not depend on the surface. So flux is given by q by epsilon naught. So it's a similar analogy for easy understanding basically. So now let's solve a question to see how we would apply Gauss law. So here in this question, we can see that there's an infinite sheet of charge whose charge density is given as rho naught coulomb per meter square, and we have to find electric field at some point p, which is at a distance r from the charge sheet. So why are we solving this question? As we know that in reality there is no infinite charges or anything like that. But if we take a case where there's a small sheet, but there's the p is at a very small distance, which is very small. So in that case, we can say that we can consider this sheet as some infinitely large sheet, and we would apply similar concept as we are going to solve this question. So how do we find this? There are two ways: one using Gauss law and one using basic integration. So by using integration, we would have taken infinitesimally small line charges and we would solve this question, but that would be a long question by using integration, and the maths would be tough. So how do we solve this question using Gauss law? What are the requirements we want to solve Gauss law? First, we need the direction of the electric field, and two, we need the charge enclosed. So what would be the direction of electric field at p? So would it be somewhat like in upward direction? But there is an equal amount of charge in upward direction and also downward direction, as this is an infinitely large plate. So if it is upward, then we are saying that there's some charge less on the upside position, but if we say that it is downside, then that is also wrong. So there is only two possibilities for the electric field at p: either it would be outward or inward. But as this is a positive charge, we know that the electric field would be outward, I mean away from the charge. So the electric field at p would be in a horizontal direction. I mean the line joining the point p and the charge sheet, the electric field would be in that direction only. So now we know the direction of electric field at point p. This is point p, and we know that the electric field at point p, or generally at any point in the whole plane, is in the let's say this is x, this is y, this is z. So it would be in the x direction. So this is only possible because the charge sheet is infinitely large. So now what surface would you take to use Gauss law? We want the charge to be enclosed by the surface, and the surface should also be perpendicular to the electric field. So if as the surface should be perpendicular to the electric field, we can take a square or we can take a circle or anything like that. But as also the surface should pass through this charge sheet for the charge to be enclosed. So by considering these things, we can take a cylindrical surface. of radius r, some radius capital R, and some length L, we know that the flux through this surface would be nothing but the the q enclosed by epsilon naught. This q enclosed is nothing but now we know that the flux is equals to E into A integral, and as we have two surfaces, one this and another one is this, and due to symmetry the electric field direction at this surface would be outward, but in the opposite direction. So comes out to be 2EA, and this A is nothing but 2E into pi r square. So now we can see that the 2E pi r square is equals to uh, rho naught into pi r square by epsilon naught. So this comes out to be, the electric field comes out to be rho naught by 2 epsilon naught. We can see that the electric field does not depend upon the at what distance the point is placed from the charge sheet. So yeah, so now by using Gauss law, uh, we we solve this question very easily. But if we would have used integration, the same result would have come out, but uh, it would have been difficult. So yeah, so now in this lecture we have discussed what is Gauss law, its applications, and we even discussed a problem which we solved using Gauss law, which made our lives very easier. And also note that Gauss law is only applicable for closed surfaces, so don't go using Gauss law and on all the surfaces in the questions, even if they are not closed. And I've also discussed an analogy to make you understand easily on how Gauss law works. So yeah, that's it for this lecture. Thank you.